Now we are going to talk about optimization. So the idea is basically the following. You have an objective function, a utility function or a cost function, and you would like to maximize or minimize this function subject to some constraints. So what is the methodology? How do we do that? So we are going to start from the basics. So what is derivative? How do we define it, and how do we find some sort of basic derivative of some basic functions? And then we are going to talk about optimization of a function with only one variable and unconstrained optimization. And then we're going to talk about two variables without any constraints. And finally, we're going to talk about optimization with some constraints. All right, so let's start. Everything starts with the differentiation or derivation. So how do we define? So suppose that I have a function f of x. For simplicity, I assume that there's only one variable, which is x. So how do I define a derivative? F prime of x, all right? Or equivalently, we write d f of x divided by dx. So here I'm not dividing anything. I'm just, this is just a way of writing the differentiation. Sometimes we write it as d dx f of x, all right? So what is the definition? So f prime of x, so the derivative of a function is defined as the following. Limit as epsilon goes to 0, f of x plus epsilon minus f of x divided by epsilon. So the idea is the following. I slightly increase, so epsilon goes to 0 means the changes I'm going to make on the value of x is very small. So I slightly increase the value of x and see how the function f is going to react to that. All right, so given that I have x versus x plus epsilon, so this is how much the function f's value is going to change by this slight decrease. And here I divide it by epsilon. It's basically per epsilon unit of change, what is going to be the unit of change in the value of the function. And here I'm taking the limit as epsilon goes to 0 because the idea is that this change is very, very minimal. All right. So therefore, the derivative of a function is basically a rate of change. Rate of change of a function. All right. So some sort of standard examples. Consider the following. F of x equals ax squared. So a is a constant. So let's apply the definition. So we know the derivative of, just side note, so f prime of x, if you take the derivative, it's basically 2 times a times x, right? So everybody know that. But let's apply this definition. So here is the idea. So I'm going to take a limit as epsilon goes to 0. But first of all, what is fx plus epsilon? So instead of x, I'm basically writing x plus epsilon. So it's a times x plus epsilon squared minus f of x, which is ax squared, divided by epsilon. All right, so the rest is basically I need to simplify this part. So this is equivalent to, so this is, by the way, f prime of x. So this is equivalent to what? Well, a multiplied by, just open this up, x squared plus 2x epsilon plus epsilon squared minus ax squared divided by epsilon. Don't forget the limit, I happen to do. And then let's keep going. Well, this is, so I distribute a over here, all right? So I'm gonna have ax squared minus ax squared, so they're gonna cancel each out. So I have again, don't forget the limit. So limit as epsilon goes to 0, I have 2ax epsilon plus a epsilon squared divided by epsilon. So this epsilon and this, and one of those epsilons will cancel out. So this is equal to limit as epsilon goes to 0, 2ax plus a epsilon. That's it. So when you take the limit of this as epsilon goes to 0, well, here there's no epsilon term. So the limit of this is just going to stay constant. But here, as epsilon goes to 0, the value of this approaches 0. All right, so therefore the limit of this term is nothing but 2ax, as we already know. All right, so well, obviously we do not use the definition of derivative every time we use we try to calculate a derivative of a function. So there are some sort of simple rules. So what are those? For example, if it is a power function, right? So f of x equals to say a times x to the power n, where a and n are some real numbers. All right. Well, in this case, f prime of x is simple. It's a times n. X to the power, we just reduce the power by 1. Right? So it's a n x to the power 1 minus 1. N minus 1, I'm sorry. If it is a natural logarithm, so for example, if f of x is equal to ln x, we use this ln function a lot, well then f prime of x is just 1 over x. As simple as this. If you are taking derivative of a sum of two functions, f of x plus g of x, all right, well then, or subtraction, well then this is basically the derivative can be distributed over f of x plus or minus the derivative of g function. All right, so whenever you have an addition or subtraction of two functions, you basically take the derivative of each individual function and then add them up, or if it is subtraction, subtract them. Well, if it is multiplication, however, well, things are a bit more complicated. D dx, f of x times g of x, for example. If this is the case, well, we first take the derivative of the first one and multiply it by the second function, plus we take the derivative of the second function, multiply it with the first one. All right, so it's basically f prime of x gx plus f of x times g prime of x. All right, so as simple as this. And finally, a chain rule. All right, so a function is a function of, sort of a function within a function. All right, so I have f of g of x, let's suppose, and I like to take the derivative of this with respect to x. So how do I do that? Well, according to chain rule, you first take the derivative of the mother function, and then leave gx inside, and then multiply it by the derivative of the inside. All right, so very simple example. There you go. So let's say your function is log x plus x squared to the power 1/2. All right. So this is sort of my g of x, but this is my f of x. F of g of x is the square root of g of x. All right, so when you take the derivative, well, first you take the derivative of the inside. It's always simpler. So the log x, its derivative is 1 over x. All right, and then plus x squared is the derivative of 2x. So because this is addition of two functions, I can just individually take their derivatives and then sum them up. So this is the inside derivative. So this g prime of x part. All right, so this is g prime of x part. And then I'm going to treat this as like x, all right? So my function is x to the power 1/2. How do I take its derivative? Well, it's simple, like 1 over half times inside to the power 1/2 minus 1, all right? So what is inside? Well, inside is this function, g of x. So the log x, I'm sorry, this is a terrible log. Log x plus x squared, and 1/2 minus 1 is nothing but minus 1/2. All right, so therefore the derivative of this term is equal to this. Right? So this term 1/2 and this term are all multiplied. So this is sort of the chain rule, and I assume that you already know all this from your sort of high school or first year calculus course. All right, so maximization. So what is the idea of maximization? Well, if I have a function f of x, all right, so I would like to maximize it, meaning I would like to find the points in its domain that gives me the highest level of f. Or if I want to minimize the function, I would like to find the point x, which is going to give me the minimum value of f within this domain. All right, so there are terms which I assume you're familiar, like local maxima, local minima, and then global maximum, global minimum. So the necessary condition for interior maximum or minimum is that the derivative of the function, when it's applied to this point, is equal to 0. All right, so this is the necessary condition for an interior max-min. So what does that mean? So if I have a function like this, let's suppose, okay, so from the interval 0, 10. All right, so this is my f of x function, and this is my variable x. Okay, so a necessary condition for interior max or minimum is that, so for example, this point where the derivative is equal to 0. So the derivative of a function, remember, rate of change, or equivalently saying it's the slope of a function. So slope at this point is, for example, positive. The slope at this point, which is basically slope of the function at this point, is 0. The slope of the function is at some point is the slope of the tangent line passing at this, a tangent at that point. So if you drove the tangent line at that point, x naught, all right, so its slope is equal to 0. So slope, for example, at this point is negative. All right, so a necessary condition for interior max or min has to satisfy this. But don't forget, the max or min can be on the boundaries. For example, in this case, this is local maximum, this is local minimum. Local in the sense that, you know, within a restricted subset of my original domain, this actually gives me the highest value within some sort of reasonable neighborhood. But the thing is, when I look at the globally, which is my domain 0, 10, this point is not really maximum because there are other points which are going to give me, for example, x equal to 10 is going to give me much higher values for f function. Okay. So sufficient condition, all right? So if an interior point is a max or min, well, then the derivative has to be equal to 0. But sufficient condition for interior local max or min is local max is the following. 1, the derivative of the function at this point has to be equal to 0, and the second derivative at this point, calculated at this point, which this is how we denoted d square f of x naught divided by dx square, has to be less than 0. All right. So this is the sufficient condition, as you remember, for interior local max, and then the sufficient condition for interior local maximum, minimum, I'm sorry, is 1. Again, the f prime of x naught has to be 0. So x naught is therefore a interior local minimum. F double prime x naught is positive. All right. So that means if x0 is an interior local max, well, then the derivative of my function at this point will be 0, and the second derivative is going to take a negative value. If it is a local min, well, then the second derivative at that point is going to take positive values. All right? So if x0 satisfies these conditions, well, then I can be sure that this point x0 is interior, local max, or min. All right? But again, is a local max, local min, as in this case, this is a local max, this is a local min. I mean, locally within some neighborhood around x0, x0 gives me the highest highest value. And again, here, if this is x naught prime, well, then within some range, okay, that gives me the lowest value. So therefore, they're interior local max and interior local min. But the thing is, globally, when I look at it, the max and the min of this function in this domain is on the boundaries. So the minimum is this 0 point x0, and the maximum is x is equal to 10. All right? Okay. Well, sometimes the first derivative may take value 0 at some point, and then the second derivative may also take the 0 value. It is the case in this example. All right, so at this point, okay, x star, the first derivative is 0 because the tangent line is just parallel, and then the second derivative of f is also 0 point. So we call this inflection point. This is neither global max or global min. Okay. All right, so the one question is like, if my domain is like negative infinity plus infinity, so basically it's this set of reals. So how can I make sure that my local maximum or local minimum is also my global maximum or global minimum? So what you need to do, you first need to solve first derivative equal to 0 equality, all right? And find the values of x which satisfy this equality. So those x's are called critical points, right? Critical points. So there may be just one critical point. If this is the case, well, then you got the the optimum point. But if there are more than one, all right, so let's say x naught prime, x naught double prime, all these 3 points do actually satisfy f prime x equals 0. All right, so the derivative at those points are 0. Well, then what you need to do, well, if you're seeking a global max, well, then look at the second derivatives. Suppose the second derivative of this is positive, f prime of x naught is positive, f double prime of x naught prime, and the other one, f double prime x prime double prime, is negative. Well, in that case, that means x naught cannot be is not local max, because remember, it's a sufficient condition. So therefore, my global maximum is either x prime, x0 prime, or x0 double prime. Well, but which one? Well, then calculate the value of f function at x naught prime and x naught double prime. Whichever gives the highest value, so if this is greater than f x naught double prime, for example, I can say, hey, you know what? This is local max. This is also local max. So within some range, this gives me the highest. The x0 prime gives me the highest value. Same here within some narrow domain. But the thing is, globally, when I consider the entire domain of this of function, well, that gives me the highest point. So therefore, this is my global maximizer. So one simple example graphically could be, I don't know, something like this. So this is the x-axis, this is f of x. So let's suppose, well, on the negative side, the function decreases. And so here I have something like this, and then this. Okay, so let's suppose this is my function. So in that case, this is x0 prime, and this is x0 double prime. All right, so if you calculate the first derivative at both these points, they're going to be equal to 0. Well, obviously, the tangent line is just horizontal. If you calculate the second derivatives, they both are going to give me negative values. All right, so both of them are local maximum. All right, so within some small ranges, they are maximizers. But globally, when I consider this function, this is clearly giving me higher values than this one. So therefore, this is the global max. All right, so for this reason, the distinction between local max or min and global max and min is important.